Okay, welcome. Today's topic is measurement and uncertainties. So, as scientists, we're trying to design experiments that give a true value from our measurements, and what we sometimes find is that our tools are a bit limited in how accurate or precise they can be, so we have to give way to having some sort of error or unknown amount built into our calculations and our discussions. So today we're going to look at random and systematic errors, absolute fractional and percentage uncertainties, and then we'll do some stuff with error calculations. Okay, so this big scary formula is here. These are listed in the IB handbook. You do not have to have them memorized, but they're also posted around the room. And our goal today is that we will understand what all of these mean and how to use them by the end of this lesson. Okay, so let's get rid of that there. Okay. So random and systematic errors. So error in measurement is expected because of the imperfect nature of both ourselves and our measuring devices. So we can talk about the precision or uncertainty in our measurement as being plus minus 1 millimeter, for example. That's just an example. It could be Celsius in temperature, it could be milliliters, could be a lot of different things. So if we look at the blue line in the example here, right here, we can see that that blue line is definitely 1 centimeter long. We'd even go as far to say that it's 1.1 centimeters long. And if you look in this area right here, it's closing in on 1.2 centimeters, but not quite there. So if we were looking at this measurement, we could say it's 1.2 centimeters or 12 millimeters long. And then we would say the plus or minus 1 millimeter, and that would be this window right here. It creates a sort of range of answers that would be acceptable for our calculations based on the imperfect nature of our measuring tools. So let's just bring this up a little bit. If you want to test this out, you can measure the width of a piece of paper and try measuring the length of your pen or pencil. You'll probably find measuring the width of the paper is significantly easier due to the hard edges versus the length of your pen or pencil, which has a few other challenges with both ends. So random and systematic errors. We'll start with random error. It's due to the recorder, so this is you, rather than the instrument. So different people may measure the same line slightly differently. This happens quite often when you are measuring with graduated cylinders and those types of things. You could have your head at different heights. You could be looking at it from different angles. One of these things is called a parallax error. And that's what's illustrated right here. So just by having your eye at different heights, you will actually come out with slightly different values for your measurement. The only way to sort of minimize these types of things is to make sure everyone's at the same height, looking at it the same way. If you'd like to try this, this is a real interesting little experiment. Sit back from your computer screen, get about at least 2 feet, 3 feet away from your screen. Put your hand up. Just take one arm, put your hand up, put your thumb up, and cover up the red shape there. Close one eye. You could start with your left eye if you like. Okay, make sure your thumb covers it up, and then open your other eye. Okay, and what you should notice is the little red shape jumps out from behind your thumb. Okay, and that's an example of parallax. Just even the distance between your eyes can cause a certain amount of parallax. Okay, so systematic error is the error due to the instrument being out of adjustment. So random error is user, systematic is more tool. So a voltmeter might have a zero offset error. So a zero offset error means that zero, when it's reading zero, it's not actually at zero. Okay, so we may have a meter stick, could be rounded on one end. So you can see here in this example, we have the portion here has been worn off. So the person, Bob, measuring with this meter stick might be getting a measurement of about 13 millimeters plus or minus 1 millimeter. But every single measurement that Bob makes with this meter stick is going to be off because of this little piece here that's been shaved off or worn off on the zero end of the ruler. So that's a systematic error. It doesn't mean Bob's measuring incorrectly. It just means the tool he's using has some deficiency or problems in it. Okay, with a ruler it's easy to see. With electronic measuring devices it's much harder to detect if there is an offset error or some sort of error that's built into the machinery. Okay, so if we have random and systematic errors, we're going to talk about the two concepts of precision and accuracy, and they're words that are interchangeable quite often in our day-to-day language, but they really mean something different in terms of our science language. So I'm actually going to start on the right side at trial 4, because this is our goal. This is always what our hope or our intent is whenever we do data collection. So this stands for random error. This is systematic error. The little down arrow means we've minimized our random error. We've minimized our systematic error. So we have a high precision, okay, and we have high accuracy. So the precision element is all of the little red dots here are grouped together. Okay, so that's precision. Accuracy means we actually hit our target. We hit the bullseye. So when we have small random error, small systematic error, we get very accurate results. Okay, so right in the middle of the target, and they're precise in that they're all very close together. Let's go to trial 3. Now we have low random error, so that's low user error, but we have a higher or increased systematic error, so that means our tools might be a bit off. So our precision again is actually quite high. Okay, because everything is grouped together. So because our random error is low, we're seeing all of the same results very consistently. But because we have tool error or systematic error, then our accuracy is off. We're not hitting the bullseye, we're hitting something off center from the bullseye. But we're hitting that location quite precisely. Okay, so now trial 2. We have an increased random error, so that's user error, and we have a decreased systematic error, which is the tool error. So if you look here, the random error, we're getting things all over the map. Okay, in terms of we're not very close to the bullseye. But because the systematic error is low, you'll notice that every one of those red dots lies in the outer ring. So it's precise in that it's hitting the outer ring, but it's random in that they're all over the ring. Okay, and then lastly, trial number 1 here. This has both high random error and high systematic error. You'll see that the red dots are not in the same ring. They're not clustered together, and they're definitely not in the center of the target. So this is the worst case scenario. This is what we try to avoid. That's low precision and low accuracy. Okay, so just a quick way to try and remember this. Systematic errors, those are usually the tools we use. Random errors are usually the user-induced errors. So these little green squares, just as a reminder, are IB questions that have been pulled from past exams, just so you can get can see what they look like. So we have an ammeter has a 0 offset error. So an ammeter is something for measuring current and electricity. So it has a 0 offset error, which means that's a type of error we need to recognize as either random or systematic. Okay, so random again is user, systematic is more tool. So this is a systematic error. Okay, this fault will affect neither the precision nor the accuracy of the readings. Well, we know that one's not true. Only the precision of the readings, only the accuracy of the readings, both the precision and the accuracy of the readings. Well, it's not going to do both because this is a tool error. So now we have to choose between B and C. So if we look back here, if we have a systematic error and low random error, we're looking at something like trial 3. So we can be precise but not accurate. Okay, so it would only affect the accuracy. Our precision could still be there. We could have very well grouped inaccurate answers. So this one here, because our precision is good but our accuracy is off, it should be C. Okay, and even when you explain this stuff, it's the interchangeability of those two words in our day-to-day language makes it tricky to talk about. So accuracy and precision, slightly different things. Okay, absolute error is the uncertainty or precision of your measurement. So if we have a student measures the length of a line with a wooden meter stick to be 11 millimeters plus or minus 1 millimeter. What is the absolute error or uncertainty in her measurement? Well, the plus minus number here is the absolute error. Okay, so the 1 millimeter is our how close we are to our target. Okay, for meter stick, it also happens to be the precision of the meter stick. The small gradations on a wooden ruler are normally millimeters. Okay, so that is also the precision. We'll talk about that more in a minute. It is important to note that absolute certainty and precision can be the same value. It can be, but it doesn't always have to be. So for example, a digital stopwatch might measure to 0.001. So that's a thousandth of a second. That's how precise it could be. But your reaction time might only be 0.1 of a second. And that would be your absolute uncertainty. Because this value here overrides how precise this tool is, your error here would just be a tenth of a second. Okay, fractional errors. This is more of a transition piece from what I've seen. We don't do a lot of fractional error off the top, but it will lead to our next one, which is percentage error. So if you look at fractional error, you're going to take your absolute error or uncertainty, and you're going to divide it by the actual measured quantity. So if you look at this, we have a measured quantity of 11 millimeters. We have an uncertainty of 1 millimeter. When we set that up as a little fraction, we get 0.09. Okay, and then you can see as the next step for this is we would turn that into a percentage error, and that's where we're going to go with this. Okay, so percentage error, we're going to take our absolute divided by our measured, which is our fractional uncertainty, and we're just going to multiply it by 100%. So this is the same calculation, only we put the 100% on there, and we find that this is a 9% error. So your measurements are within 9%, okay, of where we think they would be. All right, so if we have another green box here, a student measures the voltage shown. What are the absolute, fractional, and percentage uncertainties of this measurement? Find the precision. So if you look over here on the voltmeter, we are accurate to 3 decimal places. Okay, so 0.001 would be the smallest value we can measure. So our absolute uncertainty in this case would be 0.001. It would match up. Okay, the fractional uncertainty, if we took that 0.01 and divided it by the measured quantity of 0.385, we would get decimal 0026. Okay, if we turn that into percentage uncertainty, we're simply timesing that by 100. So we have 0.26%, so we're less than 1%. And our precision is 0.001 volts, which is the accuracy of the tool. And because these two things happen to be the same, that's okay. Now a note about precision. A digital device will have precision to the smallest number displayed on the screen, like we just did on the voltmeter. There's no ability to estimate past that. Okay, but an analog device like a ruler or thermometer, the precision is usually taken to be half, this is an important idea, half of the smallest measured interval on the device. So you can see here I have a thermometer and a ruler. So if we look at the thermometer here on this right-hand side in Celsius, these little gradations in here are worth 2 degrees. Okay, so our accuracy of our measurement here would be half of that, so we could be plus or minus 1 degree Celsius. Okay, you'll also notice on the thermometer that there's only one end that you actually have to do a reading on. The other end here is the basin that holds all of the liquid. There's no measurement on that, so you're only measuring on one end. So you can think of that as one end is active. On a ruler, however, okay, especially if we're using the millimeters, centimeter side, because the interval is 1 millimeter, we could have a precision of 0.05 millimeters, half of that interval. However, there's a little bit of a caveat with this. When you use a ruler, there are actually 2 active ends. Okay, so you're looking at, you actually are measuring or have 2 variable ends. So that we say is we have 2 times 0.5 millimeters. So the overall uncertainty is plus minus 1 millimeter. Okay, so that's where that comes from. There are both ends that are active for measuring, so that creates that extra 0.05 factored into there. All right, so let's just jump back to these scary looking formulas. So if we are adding quantities, so these are our measured quantities. These are our uncertainties over here with the little deltas. So you'll notice on this side, these guys here, these are all fractional uncertainties. Okay, and those happen when we're going to multiply or divide. And then we have something raised to a power. We have the absolute value of another fractional quantity. Okay, and if these look really scary, don't worry, they're not that hard to use. Just give me a slide or two. So to find the uncertainty in a sum or difference, so adding or subtracting, you're going to add the uncertainties of all the ingredients. Okay, so there's a couple of big things to notice here. When you're adding or subtracting in the calculation, it doesn't matter. The uncertainties are added. Okay, so uncertainties can never reduce one another. You can only compound or keep adding uncertainties together. So let's have a look at what that does. Let's hide part of this so it's not too overwhelming. Find the uncertainty in a sum or difference. You just add the uncertainties of all the ingredients. So let's start with our ladder. We have 9.51 plus minus 0.15 meter rope ladder. It's hung from a roof that's 12.56 plus minus 0.07 meters above the ground. So we have two quantities that we have to add together. How far is the bottom of the ladder from the ground? Sorry, we have to subtract. My apologies. So we're going to go A minus B. So 12.56 minus the 9.51. We get our difference right here. So this is our calculated value of 3.05 meters. Now look at these are the uncertainties. So you'll take the delta A, which is right here, 0.15, and delta B, which is 0.07. So those are those two quantities, and we add them together, and we get 0.22 meters. Okay, so let's get rid of that shade. Okay, so our overall or final result here is 3.05, which is just what we regularly would calculate, and then it's plus minus the uncertainties. Okay, and that uncertainty should cover any discrepancies or any possible variation. If we actually went out and measured this, then we should find that all of our answers should fit within that little range. Okay, so the decimal placement, this is another key piece. The decimal placement of the main data should be similar to the error values. So we shouldn't have more precision or more significant figures in our uncertainty. It can't be more accurate than our actual measurement. It's just something to keep in mind. This one here is normally 1 or 2 digits at most. So just keep that in mind. Okay, so now let's do the same thing, only let's do it with multiplication and division. So if we're going to propagate uncertainties through calculations, if we're going to use products, which is multiply, or quotients, we need to use percentage or fractional uncertainties. So I don't like all the typing straight across. I don't like expressing fractions that way, but sometimes with software it's just easier to type it in that way. So these here are all your fractional quantities. Okay, and I'll put delta y over y. Key thing to remember, the delta is the uncertainty. Okay, and the C or the value on the bottom is the actual measured quantity. Okay, so when you're looking at something like delta y over y, the delta y is the error on the overall calculation, and the y is the final result. Okay, so again, all of our uncertainties are going to be added together. They're going to make the overall uncertainty increase. Okay, and because we can't add numbers having different units, we use fractional uncertainties for products and quotients. Okay, so let's try one. It's probably easier to try one than it is to talk about it. Let's make sure there's some room here. So we have a car traveling 64.7 meters in 8.65 seconds. Okay, so what is its speed? Okay, so we're going to use V equals d over t as our relationship, so it's a quotient relationship. So we're going to take our 64.7, divide it by our 8.65. That's this piece right here. And we get 7.48 meters per second. Normally that's the easy part. Okay, now here's where it gets a little bit messy. On this line right here, the error, so you'll see delta D over D, delta T over T. So you're taking the error amount and dividing it by the measured amount in each one of these. The error amount, 0.05, divided by the quantity right there. And when you do that, okay, on the right-hand side of the equation, you'll generate this value. Okay, now if we look at the next line, delta R, just as a reminder, delta R is the uncertainty we're trying to find. So we know the calculated or measured quantity, this little r, we've got that right up here. So we can put in the 7.48, and now I'm just going to bring this down here because I think it's easier to see when it's written this way. We need to isolate delta R. So to do that, we would simply multiply both sides by 7.48. These would cancel, and we would end up with delta R equals 0.10. Okay, and that's that value right there. So our final answer would be 7.48 meters per second plus or minus 0.10 meters per second. Okay, so quick summary. The measurement tools dictate the potential precision of the data. The absolute uncertainty of the data can be the same as the precision value, or it can be adjusted based on the collection method. So if you're collecting by hand, by eye, by hearing, you may have to adjust those things accordingly. The data values will carry a certain number of significant figures, and we've gone through that. Operations with significant figures have to follow their respective adding, subtracting, multiplying, dividing rules. Okay, that was previous lesson. The uncertainty values of the data also have operational rules to follow, and that's what we just looked at today. And that's those scary formulas. Okay, so we have a task now on uncertainty. Thanks for tuning in. I'm sure there'll be questions.